Let us prove that the limit of the rational function x cubed minus 8 all over x minus 2 as x approaches to 2 is equal to 12. So we're going to use here the definition in showing the truth value of this, but of course we'll be applying important processes in order for us to arrive to our intended output. The intended output is defined in our definition. So let me rewrite the definition here just for the important part of the definition. If for every, there's no if, I believe. Okay, so for every epsilon greater than 0, there exists delta greater than 0, such that if x is an element of A, and by the way, we're talking about element of A here because the first part of the definition includes A is a subset of real numbers. Okay, that's why I just cut it out. So if you are wondering about that, you have here 0 less than delta, then the absolute value of the function minus L is less than epsilon. We need to arrive into this form, but we need to come up first with the correct delta in order for us to do that. So here, our limit of your x cubed minus 8 over x minus 2 as x approaches to 2 is equal to 12. Basically, we cannot just apply direct substitution for our c, which is 2 here, because it will become undefined. In calculus, we were able to simplify that further, and the same thing we're going to do here as well. But in the first place, this is our f of x just for the correct representation for our scratch. I'm talking about this scratch portion here, where we are going to show the correct form that we are going to substitute later on to come up with our final form here. So that would be the case, right? We're working backwards here, so please bear with me. Our f of x is x cubed minus 8 over x minus 2 minus your L, which is 12, sorry for that, must be less than epsilon. Let me remove this in the meantime and only simplify this portion so that I could come up with the presence of x minus c. Okay, x minus c in this case, our c is 2, so we will have absolute value of x minus 2. It should appear here so that we can manipulate our processes, so that we could return, and again, intended target here. Okay, so x minus 2 is in the denominator already, right? But what will happen here is we can actually have x minus 2, and you have x squared plus 2x plus 4 all over x minus 2 minus 12 here, because we could cancel that. Okay, hopefully you're following. We're canceling that. So the absolute value of x squared plus 2x plus 4 minus 12, which is actually equal to, these are all equal, right? We have here x squared plus 2x minus 8. These are all less than epsilon supposedly, because that's the intended goal. Now, since this is not possible to appear here, what if we could express this in terms of the absolute value of x minus 2? We can bound it, because x minus 2 has a boundary of delta, and at this time we can represent delta with something else. Right? So we're going to bound that, and the boundary that we're going to use here is, let us see if we could factor here x minus 2. If we're going to have x minus 2 here, can we factor that out? Let's check. X plus 4. So x squared minus 2x plus 4x. Yes, that's correct. This is less than epsilon. And by the properties of absolute value notation, this is equal to x minus 2 and x plus 4 less than epsilon. We have seen x minus 2 here already, so we can actually work for a bound into that. We're going to bound this so that this would be represented by another form. Because this is okay, this is not okay, because what we can only appear here is x minus 2. So we're going to select a representation for this. So if delta is equal to 1, following this form here, which is x minus c, or our x minus c, which is x, sorry for that, x minus 2 is less than delta. So if it's equal to 1, we can say here x minus 2 is less than 1, right? And for that, we can substitute that here for other form. But please take note of this, because that's very important as we assume that. Our goal is to come up with an x plus 4 here. So let's try to apply the absolute value properties here. Negative 1, x minus 2, and then 1. We need to have this as 4. let's come up with a 4 on that. So you could add to both sides. So you have 1, x, and 3, right? Then you can add 4 here, so x plus 4 would be here. So this would be 5, and this is actually 7. Now, let me take this only. The x plus 4 is equal to 7. So we can have here the absolute value of x plus 4 is less than 7 without considering this first. Just the idea for bounding. Okay, we are bounding that. Okay, so with this now, since x plus 4 is less than 7, so you will have this form. Okay, this form here. So your x absolute value of x minus 2 times x plus 4 less than epsilon. X minus 2, so you have here 7 less than epsilon. X minus 2 is less than epsilon over 7. So we now have two forms for x minus 2, which are actually essential to be less than delta. Okay, so if x minus 2 here is less than 1, and x minus 2 is less than epsilon over 2, where x minus 2 is less than delta, so delta could be the infimum between, what was that? 1? Yes, 1 and epsilon over 7. Okay, so we are doing all of this without proving it, but to illustrate the form for delta which could be substituted here. So this guarantees the existence of our delta needed to prove this limit statement using the definition. So we are already done with this. So with that, we can now start with our proof. So we start with the presence of epsilon greater than 0 and assume our delta be either any of this. But since both of them could be a representation, we will have here the infimum of 1 and epsilon over 7. Take note that we used 1 to get epsilon over 7, but since we let it earlier, that's a possible value for our delta. And we have here this relationship x minus 2 is less than epsilon over 7. We know that 2 is our c. So since our x minus is less than delta, so epsilon over 7 is also the other representation for our delta. Okay, so any of these two could guarantee our situation, but since we are done with that, we can proceed with our definition. Then, if this statement here, the absolute value of x minus c is greater than 0 or less than epsilon, we have, now we need to show this using our scratch work. Okay, we have the absolute value of f of x minus l is equal to this one here. We have x cubed minus 8 over x minus 2 minus 12. The other purpose of our scratch work, aside from looking for the representation of delta as mentioned, is to come up with a pattern of process, since this is guaranteed to be equivalent to this form here. So we'll be using this simpler form, equal to the absolute value of x minus 2, this one here, and x plus 4. We know this is already less than epsilon. This is what we're trying to show, less than epsilon. So we need to come up with the representation for x minus 2 and x plus 4. Now x plus 4 here is already less than 7, as identified earlier. And since this is less than, so we have here less than 7. How about x minus 2? X minus 2, okay, is also represented here, epsilon over 7. So you have epsilon over 7, sorry, that's 7, times 7, which gives us epsilon. And with this, from here, less than epsilon, we were able to structure the item we're trying to show to complete the proof. Okay, so this is it. Hence, the absolute value of f of x minus l is less than epsilon. And with that, we can now have our conclusion. Since epsilon greater than 0 is arbitrary, then we conclude that this statement is true. Okay? The limit of x cubed minus 8 over x minus 2 as x approaches to 2 is equal to, what was that again? 12. Okay? 12. this was true because we're able to structure this one here as the end part of proving limits following the definition. So again, the scratch work is very important. Aside from determining the existence of delta, it is also to help us with the rest of the manipulations here. Thank you very much for watching.